To start gluconeogenesis, we're going to begin with pyruvate. And what's going to happen is this is going to require two different enzymes to get us from pyruvate back to phosphoenolpyruvate. But we're going to do it, but two steps. So the first one is going to involve going from pyruvate to oxaloacetate. Now this reaction is actually going to happen in the mitochondria. So this is not going to happen in the cytosol, this is going to take place in the mitochondria. So this very first step of gluconeogenesis, getting us back on a pathway to create glucose, is actually going to be in a separate place. It's going to be in the mitochondria, not in the cytosol. Now in order to make this work, we're going to require ATP and bicarbonate. So bicarbonate is going to, anytime we're having bicarbonate be a substrate in an enzyme, it's going to use biotin for this to actually work. Because why? That's the hint that biotin is required. Anytime you're using bicarbonate, it's going to use biotin. Biotin is going to be covalently linked to an active site lysine. We'll talk more about biotin in just a minute. And it's going to have an allosteric activator, which is acetyl-CoA. This mechanism is very typical of biotin chemistry, so we're going to be taking a closer look at how the biotin works in this mechanism. And as far as regulation goes, when you have either high amounts of ATP or high amounts of acetyl-CoA, this is going to help stimulate pyruvate entering gluconeogenesis. Essentially, we've got all this extra energy, let's go ahead and use our energy to make a high energy molecule of glucose. So here in green, you have biotin. When you're looking at biotin, you can see that it is covalently attached to lysine. So that lysine is there in pink. It's going to be the nitrogen down at the bottom of the screen that is going to be covalently bound to our, it's going to be carbon dioxide by the time that we're done with it. So looking at this, you kind of got this notion that, okay, we're going to use biotin, biotin's attached to the lysine in our enzyme. But the grand question here is, so what do we need the ATP for? Because that ATP is not going to be attached to the oxaloacetate. We're not adding a phosphate anywhere, so what are we going to do? That ATP is going to be required for the biotin to actually be able to use that bicarbonate. Let's take a closer look. In order to get the biotin going on this, what's first going to happen is that the bicarbonate, so notice that that's not exactly carbon dioxide, that is in fact a negatively charged molecule, is actually going to do an attack on that last phosphate, and so you're going to wind up with carbonyl phosphate. Once you have carbonyl phosphate, that's going to allow the nitrogen on the end of the biotin chain to go ahead and nucleophilically attack the carbonyl carbon there of that carbonyl phosphate, which will then go ahead and release inorganic phosphate. So that's how we're using ATP. So ATP is essentially used here in order to allow the bicarbonate to be attached to biotin. But notice that when it does that, what we're actually going to get is we're really going to get essentially a molecule of carbon dioxide. So the first step of the pyruvate carboxylase mechanism is getting the biotin that extra carbon. The second step then is going to allow pyruvate, which is having some acid-base chemistry happen on another side of the enzyme. It's going to give a carbanion on that end of pyruvate, which will then allow that third carbon of pyruvate to nucleophilically attack the carbon that's now been attached to biotin. So that's going to allow us to have this final thing where we've added a carboxyl group to pyruvate. That's also going to free up that biotin and allow our enzyme to start all over again. When we're looking at biotin, notice that biotin does have that long carbon chain attached to it. So that actually also helps the biotin because this particular mechanism usually has basically like two subsites in the active site. And that long carbon chain of biotin allows that carboxyl group to switch in between those two. So here is your pyruvate carboxylase enzyme. Isn't it pretty? Some of you may have heard of biotin streptavidin. So the biotin part is the same. It turns out that avidin or streptavidin is a really potent binder of biotin. You actually find avidin in egg whites and will actually bind biotin very, very tightly. So biotin is an essential nutrient that we actually need in our bodies, but usually there's so much of it, you get it from your diet, that it's really not a problem. Unless you do something strange, like have a diet of nothing but red wine and raw eggs, because there is biotin in the red wine, but there's enough avidin in the raw eggs to attach to all of that biotin so that you don't get any of the nutrient, which has happened once. Some guy in France, apparently. Anyway, point being is that the biotin-strapped avidin linkage is actually used commonly in biotechnology. So just kind of a random side note that biotin is actually used heavily in biotech, and so you may see a biotin-strapped avidin linkage. Really common to have strep on one thing and biotin on the other, and so you need those two things to come together, and usually using biotin-strapped avidin linkages works really well. There's a deficiency. So yeah, biotin deficiency is very, very rare, by the way. Very, very rare unless you have a diet high in raw eggs, which is not very common. So pyruvate carboxylase does happen in the mitochondria. So this reaction from pyruvate to oxaloacetate does happen inside that inner membrane of the mitochondria. Now the thing though is that the oxaloacetate can't actually get out of the mitochondria. So there's actually going to be a few more steps to get those carbons back out of the mitochondria to continue on to gluconeogenesis. The thing here is that the reduction of oxaloacetate to malate is common enough that that does happen both inside that inner membrane of the mitochondria. You get the reverse to happen outside it fairly easily. So oxaloacetate is then reduced to malate. There's a malate shuttle to get malate out of the mitochondria, and then malate can be oxidized back to oxaloacetate, and then gluconeogenesis can continue on. It's thought that that compartmentalization is going to help to prevent simultaneous glycolysis and gluconeogenesis from happening. Because essentially that way it's not only just not going backwards, but you have that separation that things have to travel in and out of the mitochondria before you can actually get the reverse pathway to start going. Just a note, so for those of you that are looking at some of these structures and being like, all right, so I buy the fact that oxaloacetate can't get past the membrane, but malate looks a lot like it. So just so you're aware, malate wouldn't cross the membrane by itself either, but there's a shuttle mechanism in place that allows malate to move back and forth across the membrane. You guys will actually talk more about that in Biochem 2, but that's just a note for those of you guys who are drawing out the structures and are like, why can malate go across membranes but oxaloacetate can't? If it's just the membrane, neither one can. There's a special shuttle for malate. Pyruvate carboxylase is going to be a key step for regulation. So acetyl-CoA is an allosteric activator of pyruvate carboxylase. What this picture is trying to show you is we were talking before about glycolysis, and at the end of glycolysis we have pyruvate. If we've got oxygen, that pyruvate is going to continue on to acetyl-CoA, which can then enter the citric acid cycle. So if acetyl-CoA is low, then that's actually going to continue on into the citric acid cycle. The citric acid cycle has a lot of different intermediates that are used for a variety of other things in the cell. So if the cell doesn't have enough acetyl-CoA, then glycolysis is going to continue happening because the cell needs those other citric acid cycle intermediates, those other TCA cycle intermediates, and therefore needs acetyl-CoA, and therefore is going to keep glycolysis going. But if it has enough acetyl-CoA and the citric acid cycle is all full and everybody's happy, then there's an excess. So if there's this excess of everything in the TCA cycle, there's an excess of acetyl-CoA, then the cell essentially has extra carbons and can go ahead and funnel those carbons back into gluconeogenesis and to make glucose, which will then inhibit the citric acid cycle. You're going to see the same general notion of gluconeogenesis being activated if ATP is high, but gluconeogenesis will be inhibited if ATP is low. And this is that same general notion because pyruvate carboxylase is going to require ATP. So again, if we have enough of that high energy signal, we can get started in this anabolic reaction of creating glucose. But if ATP is low and the cell is low on energy, then it's not going to expend energy to make glucose. And you can see that both in the fact that that enzyme requires ATP. So again, high levels of acetyl-CoA and ATP indicate a high energy status. So gluconeogenesis is turned on. All of that was for the first part of the first step of gluconeogenesis. So remember that in order to reverse the last step of glycolysis, which now is the first part of gluconeogenesis, there's actually two different enzymes. So we just talked about the first one. The second one, much shorter, by the way. It's phosphoenolpyruvate carboxylase. And what's going to happen here is we have oxaloacetate. We're essentially going to swap out one of those carboxylic acid groups for a phosphate group. So what's going to happen here is with the addition of this enzyme, it's actually going to use GTP, which then will put a phosphate there and kick out carbon dioxide. Having that decarboxylation reaction is energetically favorable, so that release of carbon dioxide is going to help drive this forward, reaction forward. That hydrolysis of GTP is also going to be a driving force for this reaction. So between those two, everything's moving favorably in that forward reaction. For those of you guys who have not seen GTP, it is equivalent to ATP. So it just has a different, that different front letter, but a different nucleotide on there. So then we have the overall delta G value of negative 22.6 kilojoules per mole. So again, all moving in that favorable forward direction.